6 minutes ago, somewhere high in the Chilean mountains, a machine roughly the size of a small car finished capturing yet another image of the night sky. And with just that one frame, it added to a growing pile of evidence so bizarre that scientists are still trying to make sense of it. Because what this machine has uncovered in under a year of existence isn't a single discovery, it's a flood of them. A river of stars twice as wide as our entire galaxy. An asteroid rotating so fast it shouldn't physically hold together. A star that may have died without any explosion at all. And a visitor from another solar system that nobody even noticed until they went back and combed through old footage. This is the story of the Vera Rubin Observatory. And if you haven't heard what it just pulled off, you're about to find out why astronomers are calling it the most disruptive machine ever aimed at the night sky. Let's start with the moment everything changed. On June 30th, 2026, after 25 years of construction, testing, delays, and quiet anticipation, the Vera Rubin Observatory officially powered on its real mission. Not a test, not a preview, the actual 10-year countdown began. It's called the Legacy Survey of Space and Time. Here's what that means in plain terms. Every 3 to 4 nights, this observatory photographs the entire visible southern sky. Not one galaxy, not one star, the whole sky. Then it compares the new image against the last one it took. If a single point of light has moved, brightened, dimmed, appeared, or vanished, the system flags it instantly. Scientists at SLAC National Accelerator Laboratory confirmed that once the survey hit full operating speed, it began producing around 7 million alerts a night. 7 million, every single night. That's not a photograph. That's a live nervous system wired straight into the cosmos. To grasp how big a leap this is, rewind 1 year to June 23rd, 2025. The day the world got its first real look at what this telescope could do. Using only about 10 hours of test observations spread across 7 nights, Rubin released a single composite image of the Virgo cluster. Packed inside that one frame were roughly 10 million galaxies. Not stars, galaxies. Each one potentially home to billions of stars and countless unseen worlds. And according to NSF and Neuer Lab, that jaw-dropping figure was only about 0.05%, 1/20th of 1%, of what Rubin is expected to capture over its full 10-year survey. If 10 million galaxies already feels overwhelming, sit with this. Rubin aims to eventually observe roughly 20 billion galaxies. We've barely cracked the door open, and the room is already too vast to see the walls. But raw numbers alone don't explain why so many scientists are both unsettled and thrilled. It's what was buried inside that first batch of data that shifted the mood in observatories worldwide. Hidden in the earliest images, astronomers spotted something never cataloged before. A stellar stream stretching an estimated 163,000 light-years. Ripped away from the spiral galaxy Messier 61. That's longer than the diameter of our entire Milky Way. A structure that massive, sitting quietly in the sky, and no survey before Rubin had the width, depth, or patience to notice it. That's not a minor footnote. It's proof that galaxy-scale events have been unfolding around us all along, and we simply lacked the right eyes to catch them. Here's the part worth pausing on. Every telescope before this one worked the way a photographer does. Point, focus, capture, done. One subject, one shot, one frozen moment forever. Hubble delivered incredible detail. James Webb opened up the ancient infrared universe. But neither was built to return again and again to the same patch of sky, comparing what's there now to what was there before. Rubin was designed entirely around that idea. Scientists have started putting it a specific way. Rubin doesn't just photograph the universe, it gives the sky a memory. And a universe with memory behaves very differently than one frozen in a snapshot. It starts giving up its secrets. A missing star becomes a clue. A shifting dot becomes an asteroid. A faint smudge becomes a 163,000 light-year river of stolen stars. So if the first 10 hours of test data already produced 10 million galaxies, a hidden galactic stream, and enough asteroids to make headlines, the obvious question is, what happens once this machine runs at full power for an entire year? What about year 5? Year 10? Before we get there, you need to understand just how strange some of these early objects really are. Because one asteroid in particular is currently breaking physical rules scientists thought they understood. Stick around, because next we're diving into 2025 MN45, a rock nearly twice the height of the Empire State Building spinning so fast it should be tearing itself apart in real time. And nobody can fully explain why it isn't. Let's talk about the asteroid that shouldn't behave the way it does. Its name is 2025 MN45, and on paper it sounds like just another rock drifting through the asteroid belt between Mars and Jupiter. But once astronomers studied its behavior, it turned into one of the strangest objects cataloged in recent memory. According to a peer-reviewed study published in the Astrophysical Journal Letters on January 7, 2026, this asteroid measures about 710 meters across, nearly twice the height of the Empire State Building, tumbling through the dark. Here's the detail that made scientists double-check their instruments. This asteroid completes a full rotation once every 1.88 minutes, under 2 minutes, for something the size of a skyscraper to spin all the way around. To understand why that's so alarming, you need to know what asteroids this size are typically made of. Researchers led by astronomer Sarah Greenstreet at Noir Lab in the University of Washington explained that most asteroids in this size range are rubble piles, loose collections of rock and dust held together by nothing more than weak gravity, like a heap of gravel barely clinging together in space. A rubble pile spinning that fast should fly apart, scattering debris across the solar system. But 2025 MN45 is still there, fully intact, spinning at a speed scientists openly admit they never expected to see in an object this large. Co-author Dmitry Vavilov of the University of Washington said plainly that for asteroids around 700 meters wide, nobody expected to find one spinning faster than 10 minutes, let alone at one spinning nearly 5 times faster than that. So what's holding it together? The leading theory is almost as wild as the discovery itself. Greenstreet and her team suspect 2025 MN45 may be a fragment blasted off the dense, superheated core of a much larger planetary body that existed early in our solar system's history. A body later destroyed in a violent ancient collision. If that theory holds, this asteroid isn't just a rock. It's a surviving piece of a planet that used to exist, spinning through space for roughly 4.5 billion years, and we only just noticed it. And 2025 MN45 wasn't alone. That same research identified 19 newly confirmed fast rotators in total, all larger than a football field. 16 were classified as superfast, completing a rotation somewhere between 13 minutes and 2.2 hours. 3 were ultra-fast, spinning in under 5 minutes, with 2025 MN45 sitting at the extreme edge alongside 2 others, 2025 MJ71 and 2025 MK41. What makes this even more remarkable is the timeline. This entire dataset came from just 7 nights of observation collected back in April and May of 2025, during Rubin's early commissioning phase, months before the telescope had even switched into its real 10-year mission. This was a warm-up, a stretch test, and it already broke a record that had stood unchallenged for the entire history of asteroid science. Zoom out, and the scale becomes almost impossible to process. During Rubin's pre-survey optimization phase in early 2026, over roughly 6 weeks, the observatory identified more than 11,000 previously unknown asteroids, including 33 near-Earth objects and 380 objects orbiting far beyond Neptune. 11,000 new asteroids in 6 weeks, before the real survey had even formally begun. Now here's the number that should genuinely stop you. Scientists at Rubin Observatory and Noir Lab project that in its first full year of operation, the telescope could discover around 1 million previously unknown asteroids. 1 million. For comparison, that's roughly equal to every asteroid humanity has painstakingly cataloged over the previous 200 years combined. 2 centuries of work, potentially doubled in 12 months. Why should any of this matter if you're not an astronomer? Because asteroids aren't just floating debris, they're historical records. Each one carries physical evidence of how our solar system formed, how planets collided, migrated, and settled into the orbits we know today. Sarah Greenstreet herself pointed out that finding asteroids locked into specific motion patterns, particularly ones synchronized with Neptune's orbit, could help researchers finally trace how the outer planets drifted to their current positions billions of years ago. There's also a more immediate reason to care. Scientists are hopeful Rubin will dramatically improve our ability to detect small, meter-wide asteroids just before they enter Earth's atmosphere, what researchers call imminent impactors. Current simulations suggest Rubin could catch around one of these events per year, and instead of a few hours of warning, could give scientists a couple of days of advance notice before a fireball lights up the sky. That's enough time to point instruments at the right patch of sky, deploy sensors, and actually watch the moment of impact unfold live, rather than reconstructing it after the fact. So we now have a telescope that found a rogue fragment of an ancient shattered planet spinning nearly 5 times faster than physics comfortably allows, sitting inside a haul of 11,000 new asteroids discovered before its real mission even started. If this is what a warm-up phase produces, what happens when the same machine turns its attention to something even stranger? Something that doesn't spin or orbit, but simply disappears. Next, we're going into what some astronomers are calling the most unsettling discovery of all. A star in the Andromeda Galaxy that may have died without ever exploding, and a silent visitor from another solar system that slipped past Earth for 10 days before anyone noticed. Now we get to the part of this story that genuinely unsettled astronomers, because this isn't about something appearing in the sky. It's about something disappearing from it. Scientists call it a failed supernova, and it might be one of the strangest kinds of stellar death physics allows. Normally, when a massive star reaches the end of its life, it goes out in the most violent way imaginable, exploding outward with enough force to briefly outshine an entire galaxy. That's a supernova. Bright, dramatic, impossible to miss. A failed supernova does the opposite. Instead of exploding, the star simply collapses inward on itself and folds directly into a black hole. No blast, no flash, no warning. One moment there's a massive star, the next there's nothing where it used to be. For decades this was only a theory because catching a failed supernova is uniquely difficult. You're not looking for something bright, you're looking for an absence. A star that was there and now isn't, in a universe filled with billions of stars that all look alike until one of them quietly stops existing. According to research published in the journal Science in February 2026, astronomers pinpointed a possible candidate for exactly this kind of event in the Andromeda Galaxy, roughly 2.5 million light-years from Earth. Stephen Smart of the University of Oxford, who leads the science team behind one of Rubin's key data alert systems called LASER, said Rubin is uniquely positioned to catch more of these events because its images go about 100 times fainter than other sky surveys. In plain terms, Rubin can see the kind of quiet stellar death every previous survey on Earth was simply too weak to notice. If that Andromeda candidate is confirmed, it becomes direct evidence that some of the universe's most massive stars are collapsing into black holes silently, with no announcement at all, meaning there may be far more black holes scattered across the cosmos than anyone has ever counted. This is exactly the kind of discovery Rubin's alert system was built to catch. The scale of that system is almost hard to describe. On February 24th, 2026, Rubin ran a live test of its alert pipeline by photographing a patch of sky that already had a strong historical baseline. In a single night, it generated 800,000 alerts. Every object that changed, appeared, or vanished was automatically flagged and cataloged. Stephen Smart put it simply, everything that changed triggered an alert. And that was still just a test. Once the full legacy survey of space and time launched on June 30th, 2026, the system stepped up to its real operating scale. An estimated 7 million alerts and roughly 20 terabytes of new data every single night. 7 data broker networks around the world, including LASER, now exist purely to help astronomers sort through that fire hose in real time. One of the biggest reasons this matters comes down to type Ia supernovae, a very specific kind of exploding star astronomers use as a cosmic measuring stick. Back in the late 1990s, 2 research teams studied fewer than 100 of these supernovae and made one of the most important discoveries in modern physics, that the expansion of the universe is accelerating, driven by a still mysterious force we now call dark energy. Once Rubin's full survey is running at capacity, scientists expect to find around 250,000 type Ia supernovae every single year. Not 100. 250,000 annually. Researchers are hoping this flood of new data can finally help resolve the Hubble tension, a long-standing disagreement in physics where the modern universe appears to be expanding faster than early universe measurements predicted. If Rubin's supernova data can settle that argument, it would resolve one of the biggest open questions in cosmology. But stars aren't the only things slipping through the dark that Rubin is built to catch. It's also becoming one of the most powerful tools ever built for tracking visitors from outside our solar system entirely. In all of recorded history, astronomers had confirmed only a small handful of interstellar objects, asteroids or comets that originated around other stars and simply passed through our neighborhood before continuing on their way. One of the most recent was an interstellar comet called 3I Atlas, first announced on July 1st, 2025, after being detected by a separate telescope network called Atlas. Here's the part that genuinely surprised researchers. When astronomers went back and checked Rubin's own archived data afterward, they discovered Rubin had already captured images of 3I Atlas a full 10 days before Atlas ever announced it. 10 days. The object had been sitting quietly in Rubin's data the whole time, and nobody had looked yet. Astrophysicist Rosemary Dorsey of the University of Helsinki said scientists genuinely don't know how many more interstellar visitors Rubin might catch once the full survey is underway, estimating anywhere from 5 to 500, depending on how frequently these objects get ejected from other star systems in the first place. So think about what that really means. A telescope that can retroactively notice a visitor from another star system 10 days after it already passed by, unnoticed, in real time. A star in a neighboring galaxy that may have died in complete silence. An alert system processing 7 million changes to the sky every night. More information than human astronomers could ever fully process on their own. This isn't a telescope anymore. This is a live surveillance system for the entire visible universe. And yet, everything we've covered so far, the asteroids, the vanishing stars, the interstellar visitors, is still just the visible layer. Underneath all of it lies the real reason Rubin was built in the first place, and it has nothing to do with what we can see. In this final section, we're heading into the invisible universe itself, dark matter and dark energy, the forces that make up the vast majority of everything that exists, and why scientists believe this observatory may finally answer questions humanity has been chasing for over 90 years. Everything we've talked about so far, the galaxies, the asteroids, the vanishing stars, the visitors from other solar systems, is all part of the universe we can actually see. But here's the number that should make you sit back in your chair. Everything visible in the cosmos, every star, every planet, every galaxy, every human being who has ever lived, makes up only a small fraction of what actually exists. The rest is made of dark matter and dark energy, two forces that dominate the universe and that scientists still can't directly explain. And this is where the story becomes personal, because Rubin was built specifically to hunt for them, and named after the woman who first proved they were real.